climate closure is the end of the scientific part of the debate about global warming. At the moment, there are two explanations. The first one, that is supported by almost the entire scientific community since the 1980s or so, or earlier, is that the warming we've experienced over the last 100 years or so, associated with the period of heavy use of fossil fuels, coal and petroleum, that the CO2 that they have emitted, their burning, has made a kind of a greenhouse around the Earth. It has made a layer of CO2 that traps heat from the Earth, prevents it from leaving, and therefore raises the temperature of the Earth, much like a greenhouse does. The only thing is that there has been an alternative theory that has been supported by climate skeptics, which essentially says that we've just witnessed a giant natural fluctuation. In other words, might be the sun that suddenly, for some reason, increased its output and therefore warmed the Earth up over the last 100 years. It might be volcanoes have stopped exploding as much as they did before, because when a volcano erupts, it can cool the Earth down by putting lots of small particles in the stratosphere that reflect sunlight. Or it could be some kind of internal variability, and they just say, well, from time to time, the Earth just warms itself up. And so that's what climate closure is about. It's trying to come to the end of this debate.
How can we resolve the debate between the two explanations for the warming?
Well, we've got to remember that science not only tries to prove theories to be true, so true theories, we try to find all kinds of evidence and make the theory as convincing as possible if it's true, but science also disproves theories that are false. We do that all the time. In fact, much more frequently than trying to prove a theory true. There are lots more wrong ideas than right ones. And so the problem is, to prove a theory is true, it can only be proven beyond reasonable doubt. So even the fact that, or the idea that the sun will come up tomorrow morning, that if somebody wants to be completely skeptical, the only way to convince them is wait till tomorrow morning. You can bring all the evidence you like, make it as convincing as you like, but it's still not completely proven. However, a theory can be disproved by a single experiment that shows it's false.
Is this like medical testing?
It's a lot like medical testing, exactly. So the human body is extremely complex, and all kinds of medications and therapies have been developed for curing everything from cancers to toothaches. And we actually don't have to know how the body works in order to be able to evaluate these therapies and medications. We just need two groups. We could have two groups which have essentially the same cancer, for example. We give one group the new medicine that's being proposed, and we give another one essentially sugar pills. And if after a certain amount of time the results are the same number of people are dying or have the cancer in both cases, nothing changes, then we can reject the medication even without understanding anything about the body, the way the body works. So that's what we're trying to do with climate closure. We're trying to disprove the giant natural fluctuation hypothesis. And since there are only two explanations for the warming, either it's human or it's natural, if we can disprove the natural hypothesis, then that just leaves the human one as the only plausible explanation. And so that's what climate closure is about.
How did the temperature vary before industrialization, and massive burning of fossil fuels?
Well, you're right. We need to have a kind of a control group. If we're going to judge whether the temperature in the last 100 years is doing something normal or something strange compared to the past, we have to know how the temperature varied before we started pumping lots of carbon dioxide into the atmosphere around the end of the 19th century. So what we've got here is 125 years of temperature variations, in this case from 1500 to 1624. 125 years because that's roughly the length of time since we've had the warming. And this 125-year period, of course, is way before we started burning fossil fuels to any extent. So we're seeing more or less the unperturbed behavior of the atmosphere without significant human influence. And you can see the way the temperature is varying. I've put the average here as the axis, so it's varying around that axis. But you can just take a look at the way that it varies. We can take a next 125-year period, and we can see that they're not so different in their statistical character. The bumps and wiggles are a bit different, but they're roughly doing the same kind of thing. The third 125-year period is also fairly similar. And this takes us more or less to the beginning of the era of strong fossil fuel burning. And before we go on, we can already note that over 125 years, the temperature has typically been changing by about 0.2 degrees. We can do some statistics on that, and it turns out it's about 0.2. So now we can compare with the recent period, the period since, say, 1880, when we had more and more fossil fuel burning, and you can see that the temperature is going right off chart. And in fact, we've had about 1 degree of warming since then. So the question I'm going to try and answer is, what is the probability that that top curve, the recent curve of 1 degree, was just a kind of a chance big fluctuation compared to the more typical 0.2 degree fluctuations we see below?
How can you know the probability of giant natural fluctuation?
Well, the normal way that statisticians would approach the problem is they would go to the bell curve. Bell curve looks something like, well, it's exactly like this blue curve in the figure here. What I've done is I made a bell curve that has a width of 0.2 degrees. So that would be a curve representing the typical fluctuations in the pre-industrial era. And then at the bottom, you can see there's a red arrow that shows roughly the 1 degree warming that we've had in the industrial period. And you can see the probability is so tiny that it's right along the axis there. We can't actually read what it says. In fact, that probability is so small that it's about 1 in 3 million of that 1 degree change occurring. One chance in 3 million is about your chance of being struck and killed by lightning in any given year. Not a very likely proposition. Now, in order to see what's going on there a little bit better, we can plot the same bell curve in this other representation where I've blown up the probability axis using logarithmic coordinates. And now you can see that the 1 degree warming it does indeed correspond to a very small probability.
But the bell curve doesn't allow for extreme events, and everyone knows that the weather can be very extreme, so why should the global temperature follow the bell curve? Shouldn't we expect extreme events?
Well, yes, we should. And so using the bell curve is not really very convincing. And in fact, there's a reason why we should get extreme events, and it's called the multifractal butterfly effect, represented here by a whole bunch of butterflies flapping their wings. It's just a kind of a metaphor because anything that's distributed in space that could give small perturbations to the atmosphere could be responsible for this. What happens is that the atmosphere is so unstable that the flapping of the wings of butterflies can destabilize it, and then the small scales being destabilized can destabilize something larger and larger structures, and we can get ultimately extremes that we wouldn't have expected otherwise. And in fact, the multifractal butterfly effect leads to something called black swan extreme events. So why black swan? It's because white swans were always considered a metaphor for the sort of the normal and the ordinary, and black swans were considered, even by the ancient Greeks, to be something that's completely impossible. However, when British explorers discovered Australia in the 17th century, they discovered a new species of swan, which was a black swan. And since then, a black swan then has become a metaphor for sort of an out-of-the-box event, something that you wouldn't have imagined because your thinking is too blinkered. In this case, it's thinking in terms of bell curves. You're going to be missing these extreme events, which actually are important.
Mm-hmm. With black swan extremes, shouldn't we expect giant natural fluctuations? Maybe the skeptics are right, after all.
Well, absolutely, we have to check to see how probable those 1 degree fluctuations are. And we have to take into account that we have some information from past data that allows us to actually check the probability distributions directly. So I've come back to the picture I showed before, the bell curve, and now what I've done is I've put the real data, pre-industrial data, on top of that. It's actually the black dashed line that you can barely see. It's sandwiched between two orange curves that give you an idea of how confident we are about the placement of that black line. And once again, on the left-hand side, you can't really see much difference with the bell curve. But when we blow it up on the right by stretching out the probabilities, then you can see that there's actually a much higher probability of having a 1 degree warming than it would be if it was the blue bell curve. So if we had the dashed black swan event curve, actually we would find a probability 1,000 times larger, 1,000 times more likely to have a 1 degree warming than if it had been a bell curve. But 1,000 times more is still only 1 in 3,000 instead of 1 in 3 million. So rather than this being the probability of you being struck and killed by lightning in a given year, it's the probability of you dying from poisoning in a given year. So that's a lot more likely than lightning, but for most of us, that's still pretty unlikely, and it won't stop us going about our daily business. We would just neglect probabilities that low. And so the same is true then for the giant natural fluctuation hypothesis. We can just safely ignore that possibility. It's just way too unlikely to be true.
If the concentration of CO2 increases, then the amount of energy the Earth receives per year also increases. If CO2 is so important, shouldn't the temperature increase in proportion to this forcing?
Well, once again, yes, we expect that to be true, and this graph actually shows that it is true, because what I've done is I plotted the global temperature since 1880, not as a function of date the way we're used to, but by a function of the forcing, the amount of extra energy per time that we get because we put all that CO2 into the atmosphere. And you can see that the relationship is indeed very straight. I put a straight black line through the middle of that, and the zigzags about that line are essentially just natural variability. And what you can see here is that in the last period since 1998, that things have more or less flattened out a little bit. And this fact has been seized upon by the climate skeptics to say, oh, that the temperature, the global warming has stopped. They say, just look at the plot. It's basically just flat now. We're not having an increase over the last decade or so. But when you look at this graph, you can see exactly what's going on. What they call the pause, shown here by this arrow from 1998, is simply the follow-up to this massive pre-pause warming. From 1992 to 1998, there was a huge, about a 0.4 degree increase. And all we're doing is pretty obvious from this plot, is just returning to the long-term black line trend. So what that means is we've had a kind of a natural cooling following this huge natural warming that is just compensating more or less for the anthropogenic warming. And so the pause is just a pause, no more.
Can we use the previous straight line to predict the warming? So,
well, if we go back to 1909, let's say that over 100 years ago, we had known the slope of that line. Let's say that that's the effective climate sensitivity. Let's say we knew the temperatures before 1909, let's say from 1880. And let's say that our economists back then had given us a good scenario about economic development from which we could deduce the amount of fossil fuels that would be burned and deduce how much of that would end up in the atmosphere, and we could deduce the CO2 concentrations. In that case, we could have predicted that from 1909 to 2020 even here, that the temperature would go as that smooth black line in the middle. And we could also say that with 90% of the time it would be between the dashed lines. And you can see quite clearly that the temperature actually did exactly that. And so, in other words, everything, including the pause, is pretty much as expected on the basis of the CO2.
So, what are the most important things to remember?
Well, the first one is that we've had about 1 degree of warming since the 19th century. The second one is that the probability that this was no more than a giant natural fluctuation is less than 1 in 1,000. So we might as well just forget it. It's much too unlikely to be the explanation. The only explanation that is plausible at all is that we've done it. Essentially, it's CO2. And in fact, using that, there's such a strong relationship between the CO2 concentrations in the atmosphere and the warming that we could have actually predicted 100 years ahead of time the temperature in the 21st century. And so the pause, in fact, is just a pause, no more than that. And the temperature, unfortunately, is going to just continue to increase as our CO2 levels increase. Thank you.
Thank you.